Hey, I've been hearing a lot about analog electronics lately. Can you break down the basics for me?
Sure, analog electronics is all about dealing with continuous signals. The foundation of this field is circuit analysis. You've probably heard of Ohm's law and Kirchhoff's laws, right?
Yes, I know the basic concepts of Ohm's law. But can you explain Kirchhoff's laws in more detail?
Absolutely. Kirchhoff's current law, KCL, states that the sum of currents entering a node must equal the sum of currents leaving the node. It's based on the principle of conservation of charge. Kirchhoff's voltage law, KVL, on the other hand, says the sum of all voltages around a closed loop must equal zero, reflecting the conservation of energy.
Got it. So, how do we apply these laws when analyzing circuits?
For simple circuits, we can use Ohm's law to solve for unknowns. For more complex circuits, we might use nodal analysis, where we assign voltages to the nodes and solve for them using KCL. Superposition is another method. When multiple sources are involved, we analyze each source independently and then sum the effects.
Interesting. You mentioned dynamic circuits earlier. How does transient analysis work in these circuits?
In dynamic circuits, we have components like capacitors and inductors that store energy. Transient analysis looks at how voltages and currents change over time when these components interact. It's critical for understanding how a circuit behaves right after a switch is turned on or off.
So it sounds like transient analysis is important for real-world applications. Moving on, I've also heard a lot about amplifiers. How do amplifier circuits work?
Amplifiers are used to increase the amplitude of a signal without distorting its original waveform. The key components are semiconductor devices like BJTs, bipolar junction transistors, and FETs, field effect transistors. In amplifier circuit, we use these to control current or voltage in a way that amplifies the input signal.
I see. You mentioned BJTs. What's the difference between the common emitter, common collector, and common base amplifier configurations?
Great question. The common emitter configuration is the most widely used. It provides voltage gain and inverts the signal. The common collector, also called an emitter follower, doesn't invert the signal, but provides high current gain. The common base configuration, though not as common, provides a low input impedance and high voltage gain.
So it's a trade-off between voltage gain, current gain, and inversion, depending on the configuration?
Exactly. Each configuration has its use cases. For example, the common emitter is great for amplification in audio circuits, while the common collector is better for impedance matching.
That makes sense. What about operational amplifiers? I hear they're used a lot in analog electronics.
Yes, op-amps are fundamental. They have high input impedance and low output impedance, which makes them versatile. They're used in a variety of circuits like inverting and non-inverting amplifiers, integrators, and differentiators.
What exactly is the virtual short and virtual open concept with op-amps?
The virtual short refers to the condition where the voltage difference between the two input terminals of an ideal op-amp is zero. This happens because the op-amp adjusts its output to make the voltage difference negligible. The virtual open condition is when the input terminals are effectively isolated in terms of current, but the voltage difference is still zero.
I think I understand now. So op-amps can be used in many applications, right? Can you give me an example of a nonlinear application?
Sure. One example would be a comparator. An op-amp used as a comparator switches its output between two levels, depending on which input is higher. This is useful for things like signal threshold detection, such as turning on a light when the ambient light level falls below a certain threshold.
Got it. Now, how about DC power supplies? I've heard there's a distinction between linear and switching regulators.
Yes, there's a significant difference. Linear regulators are simple and provide a stable output voltage, but they're inefficient because they dissipate excess power as heat. Switching regulators, on the other hand, convert power more efficiently by using inductors and capacitors to step up or step down the voltage, but they tend to be more complex.
So linear regulators are good for low-power applications, and switching regulators are better for high-efficiency needs?
Exactly. Switching regulators are often used in battery-powered devices because they maximize battery life. Linear regulators are more common in applications where low noise and simplicity are more important.
Thanks for the overview. Now shifting gears a bit to digital electronics. What are the basic building blocks in digital circuits?
The foundation of digital electronics is binary logic. You start with basic number systems, like binary and BCD, and from there you use Boolean algebra to design logic circuits. The primary building blocks are logic gates, AND, OR, NOT, and their combinations.
I know about logic gates, but how do they work together in combinational logic circuits?
In combinational logic, the output depends only on the current inputs. We use gates like AND, OR, and NOT to create more complex logic functions, like multiplexers, encoders, and decoders. These circuits don't have memory, they just compute an output based on the inputs.
So, the behavior of a combinational logic circuit is entirely determined by its inputs?
Exactly. There's no feedback or state retention in these circuits. For example, in a multiplexer, the output is determined by the selection lines and input signals at that moment.
What about sequential logic circuits? I've heard they can store information.
Yes, sequential circuits have memory, meaning the output depends not only on the current inputs but also on the past history of inputs. This is where flip-flops come in. Flip-flops are basic building blocks for memory storage, and we use them to create counters, shift registers, and other devices that require state retention.
I see. So flip-flops are the core components of sequential logic?
Exactly. The most common types of flip-flops are the SR, D, JK, and T flip-flops. They each have different ways of handling input and output based on their states, which makes them suitable for different applications like counters or memory devices.
That makes sense. I've heard a lot about FPGA and PAL devices in the context of programmable logic. What are they and how do they differ?
PLDs, or programmable logic devices, are integrated circuits that can be programmed to implement a wide variety of logic functions. PALs, programmable array logic, are simpler, using fixed AND arrays and programmable OR arrays. FPGAs, field programmable gate arrays, on the other hand, are more complex and allow the user to configure a vast number of logic gates with more flexibility, making them ideal for more intricate designs.
So FPGAs offer more flexibility and are suited for complex applications, while PALs are simpler and often used for smaller tasks?
Exactly. FPGAs are used in high-performance applications like digital signal processing and hardware acceleration, while PALs are more cost-effective for simpler tasks like controlling LEDs or switches.
That clarifies things. Now let's talk about the practical applications. What's involved in mixed signal systems?
Mixed signal systems integrate both analog and digital components. Like in a temperature monitoring system where you might use an analog sensor to measure temperature and then convert that signal into a digital format for further processing or display.
So you're combining the precision of analog with the processing power of digital?
Exactly. The challenge is ensuring that both analog and digital parts work together seamlessly, without too much noise or signal degradation.
And when designing such systems, are there specific engineering considerations to keep in mind?
Yes, noise immunity is crucial. Analog signals are more prone to interference, so careful layout, shielding, and filtering are necessary. Power optimization is another concern, especially in battery-operated devices, where you want to minimize consumption while maintaining performance.
It sounds like designing these systems is a balancing act between performance, power, and noise control.
Exactly. It requires careful planning, testing, and iteration to get everything working together.
That's a lot to consider. When it comes to experimenting with these systems, what tools are commonly used for simulations?
Simulation tools like Multisim and Proteus are widely used for both analog and digital circuit design. They allow you to test your circuits virtually before building them physically. For more complex designs, especially in digital electronics, tools like ModelSim or Xilinx Vivado are great for FPGA programming and simulation.
I've heard about these tools. Are there specific advantages to using one over the other?
It really depends on what you're designing. Multisim is fantastic for beginners and for simulating simple analog circuits because of its intuitive interface. Proteus is better for both analog and digital, and it's also great for testing microcontroller-based designs. For FPGA design, Vivado offers the full suite of tools for simulation, programming, and debugging, but it's more complex.
I see. So for FPGA, Vivado is a go-to tool. How about for smaller projects or educational purposes?
For smaller or educational projects, I'd recommend starting with something like Tinkercad, or even using simpler software like Logisim. These tools are easier to learn and let you focus on basic concepts of logic and circuit design, without getting overwhelmed by the complexities of professional software.
Those sound like great starting points. Now, when you talk about FPGA programming, how do you actually program an FPGA?
FPGA programming typically involves writing code in hardware description languages like VHDL or Verilog. Once the code is written, it's synthesized into a bitstream file, which is then uploaded to the FPGA. The FPGA's internal configuration is modified based on the bitstream, and it starts performing the intended logic operations.
So, VHDL and Verilog are the primary languages for FPGA development. How do they compare?
Both VHDL and Verilog are used to describe hardware, but VHDL is more verbose and offers a higher level of abstraction, which can be good for large projects. Verilog is more concise and closer to C in syntax, making it easier to learn for those with a software background. Both have their strengths, but it often depends on personal preference and the project requirements.
Interesting. And once the FPGA is programmed, how do you test its functionality?
Testing is done through simulation first. After that, you'll test the actual hardware using test benches or an oscilloscope to monitor the outputs. For more complex projects, debugging tools integrated into software like Vivado or using a logic analyzer can help capture and analyze the signals in real time.
It sounds like the testing process is thorough. Moving back to the digital side, what's the role of flip-flops in sequential logic circuits, and how do they affect the timing of the circuit?
Flip-flops are key to controlling the state of sequential circuits. They store a single bit of information and change their output based on the clock signal. The clock dictates when the flip-flop updates its state. In circuits like counters or registers, the timing of the clock signal is crucial for synchronized data processing.
So, the clock controls the flow of data in sequential circuits. How do you handle timing issues like race conditions or glitches in these circuits?
Race conditions and glitches can occur if signals propagate through the circuit at different speeds, or if timing isn't properly managed. To prevent this, you can use techniques like clock gating or proper synchronization with edge-triggered flip-flops. Additionally, ensuring that your timing constraints are met during design and simulation helps avoid these problems.
I see. So timing and synchronization are critical to avoid errors in sequential circuits. When designing a digital circuit, are there any common pitfalls to look out for?
One common pitfall is not considering the propagation delays of gates, especially in large circuits. If the timing of your signals isn't properly accounted for, the circuit may malfunction. Another issue is improper power management, which can lead to unreliable performance or damage to components. It's important to thoroughly simulate and test your designs under different conditions.
That's very helpful advice. Now, looking toward the future, are there any emerging trends in analog or digital electronics that we should keep an eye on?
In analog electronics, there's a growing interest in low-power, high-efficiency designs, especially as the demand for portable devices increases. In digital electronics, AI and machine learning are driving demand for more specialized hardware, like neuromorphic computing and custom FPGAs for specific tasks. The rise of quantum computing is also something to watch, as it might disrupt both analog and digital circuits in the future.
It sounds like there's a lot of exciting innovation coming. How do you think AI will impact circuit design specifically?
AI is already having an impact by helping with optimization and automating parts of the design process. For example, AI-driven design tools can automatically tweak circuit parameters for optimal performance or efficiency. AI is also being used to accelerate testing and verification processes, making the overall design flow faster and more accurate.
That's fascinating. So, AI could really streamline the entire design and testing process. What do you think about the future of mixed signal systems in this context?
Mixed signal systems are becoming more integrated with the rise of systems-on-chip society designs. I could play a huge role in optimizing these systems for both analog and digital performance, especially as we move toward more complex and compact devices. These systems will likely become even more powerful, with AI enabling better signal processing and adaptive behavior.
It seems like the boundaries between analog and digital are blurring more and more. So for someone just getting started in electronics, What's the best approach to stay up to date with these trends?
The best approach is to stay curious and hands-on. Keep experimenting with new tools and technologies, and don't be afraid to dive into simulation and real-world projects. Also, subscribe to industry journals, attend conferences, and participate in online communities to stay connected with the latest developments.
Thanks for all the insights. I feel like I have a much better understanding of both analog and digital electronics now. This was really helpful.
Glad I could help. It's a fascinating field, and there's always something new to learn. Keep exploring and experimenting.